Hi guys, welcome back to my channel. So today we're going to be talking about the comparison tests for series, and these are used to determine convergence or divergence for a series. And as you hopefully remember from our previous discussions about series tests, they're not all equally useful. So given a series, you have to strategically assess which test is going to be most useful for telling you something about the series. So between our two comparison tests, there is the first type, the regular comparison test, and then there is the limit comparison test. So between the two, it all depends on what you're seeing easier. So if you can see an inequality that you can relate to your series, and you're looking to relate the series you are trying to show as convergent, divergent to a series that you know something about. So you want to think harmonic series, p-series, geometric series, some series that you know on a very elementary level to be either convergent or divergent. Then in that situation where you can see an inequality that's true, that's when you would use the comparison test. And if you're not sure if your inequality is true, that might be a sign that either your inequality is untrue or you just don't have enough information to utilize the comparison test. So there is another kind of comparison test, the limit comparison test. And the limit comparison test is going to be most useful when you have a series that you're fairly confident is very similar to your series that you know the convergence or divergence of. So again, you want to know before you compare the series you're trying to show convergence and divergence, you want to know the behavior of the series that you're comparing it to. For both of these tests, you'll want to know the behavior. But the limit comparison test allows you to demonstrate that they are similar with a limit. Let's say you chose a series that is not actually that similar to the series that you're looking at. Your limit comparison test will just not prove to be helpful. So when you try and run the test, you won't get a conclusion from it, basically. Okay, so let's take a look at some series where we're going to utilize these and just see what tends to lend itself better to one versus the other. So for our first example, we're going to determine and prove whether the series sine k over k cubed plus 1 is convergent or divergent. Okay, so the first thing that jumps out at me about this series is the sine function. So whenever I'm looking at my basic trig functions, such as sine and cosine, I am seeing that I can compare this series to a series that relates to -1 and 1. Okay, the reason I would be thinking about doing that is because I know that sine is bounded. So I can say right away that sine of x is less than or equal to 1, and it's greater than or equal to -1. And that's always true, no matter what's in the argument for the trig function. So because of that bounding, I can say that sine of k cubed plus 1, that must be less than or equal to 1 over k cubed plus 1. And I can be really confident about that inequality because I've kept the denominator the same and I've just changed the numerator. So I'm confident in that inequality being true. Next, this is almost like a series that I know something a lot about. It feels very much like a p-series to me. Do you guys see how it's almost 1 over k cubed? Perhaps there is an inequality that can relate us to 1 over k cubed. Fortunately, k cubed plus 1 is a bigger denominator than k cubed would be. Okay, think about that, because k is always positive. Adding 1 will make it a bigger denominator. So that means that 1 over k cubed plus 1 would be smaller than 1 over k cubed. We kept the numerator the same. We made the denominator smaller. So it's like comparing like a quarter to a half, right? The smaller the denominator of the fraction, the bigger the number actually is. So there's an inequality that relates our original series, sine k over k cubed plus 1, to a p-series that we know something about, right? Because I know that a p-series would be convergent for the power 3 on the bottom. So I'm going to disregard that middle step here. We'll just kind of highlight the relevant inequality that we're looking at. So we know our original is less than or equal to 1 over k cubed. And we know that the series 1 over k cubed, k ranging from 1 to infinity, is a convergent P series. So because our series sine k over k cubed plus 1 is less than or equal to by our comparison test, our original series sine k over k cubed plus 1 converges. Okay, so a couple details to note. One thing that is often not written because it's kind of customary, and a lot of times once you get used to a fact being true, it's kind of like the detail is omitted from explanation, but I'll just make a side note here that this inequality has to be true for all k. Okay, and the way that we didn't specify that the inequality was true for certain k values implies that. So when you write that inequality, you are implying that it is true for all k. Otherwise, you would have to specify not, if that makes sense. So it goes without saying the way we wrote it that it was true for all k, but you want to be confident before you use this comparison test that that inequality does have to be true for all k. So where you want to be careful is when you're looking at things that can be positive and negative. So fortunately for us, that wasn't an issue with this particular series and what we were able to compare it to, but there's definitely some times where you'll need to be thinking about that detail. Okay, so let's take a look at another example. For our next example, we're going to determine and prove whether the series n squared plus 1 over n cubed plus 1 is convergent or divergent. So when I look at this series, I'm definitely thinking comparison. I know I'm going to compare it to something because it feels almost basic, right? The only thing that's throwing it is the plus ones. So I can kind of highlight those. If you imagine discarding the plus 1, this series looks like it's going to behave an awful lot like 1 over n because it's kind of pretty similar to n squared over n cubed, which reduces to 1 over n. So I know the series that I want to relate it to, but because there's a plus 1 on the numerator and the denominator, trying to mess around with inequalities for this one is going to be just a little bit harder than the last one. Like, I'm not saying it's impossible, just saying that it feels a little bit harder, right? So in this case, I think for me personally, the easier option is going to be the limit comparison test. So let's run the limit comparison test, and we're going to go ahead and compare it to, we're going to let our Bn be our harmonic series. So why would we choose 1 over n? That's a pretty basic series we know something about, and hopefully you recall that the harmonic series is divergent. It's one of the first and most famous examples of a divergent p-series. Okay, so let's take a look at the limit comparison test. So when you're setting up your limit comparison test, you want to think about the series that you're trying to figure something out about. That goes in the numerator, and the series that you actually know something about, convergence, divergence, that you think is similar to your series, that goes in the denominator. So I'm going to take the limit as n goes to infinity of my unknown in the numerator and known in the denominator. I have a ratio of 2 fractions, so we're going to clean that up. We've got multiplying by the reciprocal. This ends up being the limit as n goes to infinity of n cubed plus n over n cubed plus 1. And hopefully you can tell, looking at that, we've practiced on limits quite a bit now at this point, that the limit there is going to be 1. If you're not sure about this, you can definitely factor out the n cubed. That's probably the fastest way of seeing that limit and reduce, right? Okay, so our limit is 1. And let's go back to our limit comparison test, what that means. We got a positive finite value. So these series behave similarly. And because our comparison series, the harmonic series, is divergent, our series is divergent. Okay, nice. And this is another great example of something else that can confuse students. So sometimes they forget about the difference between a sequence and a series, and they'll say, oh, well, this converges because 1 over n converges. And it's like, well, the sequence 1 over n converges, but the series 1 over n definitely does not. So make sure that you are thinking in your mind about the difference between sequences versus series. Be careful in that detail.